Hi everyone, this is going to be a lesson for Calculus 1 on extreme values of functions. Before we start, one thing I wanted to say is we're beginning kind of a new topic where the next few sections are all going to pretty much be about the same thing. And there are a bunch of definitions. So I went ahead and typed some of the definitions up for you. And there's a definition sheet that's posted in the place where you usually get worksheets. So if you go to where I post worksheets, you'll see chapter 3 definitions. And some of them are going to be covered in this lesson, and some of them are going to be in the next 2 lessons. So you don't have to worry about the entire sheet today, but in the upcoming lessons, we'll get to all of it. Okay, that's all I wanted to say. So let's go ahead and get started. All right, so extreme values of functions. What do you think that means just from the title? How can a value of a function be extreme? Well, it's basically going to be the largest value or the smallest value that a function has. We're going to go into a little bit more detail, but that's fundamentally that's the idea. And these sections are basically going to be an application of the derivative, right? So things that the derivative can help us find. Let's start with some definitions. We're going to start by saying let f be a function with domain D. You know, the domain is a set. The domain might be all real numbers, or the domain might be some smaller portion of the real numbers. Then f has an absolute maximum. I'm going to underline that. At C if. First of all, let me tell you what we're trying to get at with this definition. We're trying to talk about the largest value of f. Well, it's the maximum value of f, so it makes sense. We're trying to talk about the largest value of f. So how can we write a definition for this? Well, it occurs at C, so we're going to say f of x is less than or equal to f of c for all x in D. And an absolute minimum at C if f of x is greater than or equal to f of c for all x in D. Let's look at these definitions. Make sure that these definitions make sense to us. So if we want to talk about a function value, you know, an f of c value, we basically want it to be largest or smallest, so we use inequalities. It makes sense. We're saying that it's f of c is greater than or equal to all other f of x's. On this one, f of c is less than or equal to all other f of x's, so it's the smallest or the minimum. Okay, now a little bit of terminology. The plural form. By the way, notice that this says an absolute maximum, an absolute minimum. It doesn't say the absolute maximum, the absolute minimum, because a function could possibly have more than one. And you might say, well, how can there be more than one greatest value? And the answer is they could be tied. They could be tied for maximum, right? Because there's a less than or equal to symbol. So you might have a function that goes up to some maximum value, comes back down, and goes back up to the same maximum value. So it could occur in more than one place. So we could possibly need to talk about this in a plural sense. There's more than one of them. And when there's more than one, we call them minima and maxima. So the absolute maxima of a function or the absolute minima of a function. We might also want to talk about We might want to talk about them together as just an overall concept, like the concept of minima and maxima, and together we refer to them as extrema. I'll say in parentheses, or extreme values. And sometimes for terminology, sometimes the word global is used. Global instead of absolute. We use the word absolute to mean, it's the absolute largest value. We're not talking about it like absolute value bars. It has nothing to do with absolute value bars. It's more about being the single greatest. I guess I shouldn't use the word single because I just said there could be a tie. So anyway, it's the greatest or the minimum. So we can call it the global maximum or a global maximum or a global minimum. Global and absolute mean the same thing to us. I'll show you an example. Let's get to an actual concrete example here. And for an example, I'm going to use f of x equals x squared plus 1. And this has domain, all real numbers. We could draw a picture of this. Maybe from a picture we could see where the greatest value is, if there is one, or if there are absolute minima or maxima. So we go 1, 2, 3, 4, 5. Let's say that's enough. So you could draw this, right? You know the y-intercept is 1. And other than that, it's x squared, but it's shifted up 1 unit. So x squared is a parabola. You know some points that it usually passes through. It usually passes through 2, 4, but it's been shifted up 1 unit. So I'll go to 2, 5. All right, so this is what the function looks like. And I'll label some things for scale. We're going to be drawing functions quite a bit in the next couple of sections. So you want to get good at drawing functions. When we draw functions, we should label the x-axis and y-axis. You should put a couple of numbers on each axis to indicate the scale. That's important because if you don't do that, then you have no idea what kind of scale you're trying to convey. Anyway, what can we say about the extrema of this function? Well, I'm going to say that f has an absolute minimum at x equals 0. Because, oh, and by the way, 0, you could say in the definition, 0 is basically my c value. Sometimes we call it x and sometimes we call it c. But there's an absolute minimum at x equals 0. Why am I saying 0? X equals 0 is here, right? Look at what's going on with the curve above x equals 0. It's the lowest point on the curve. Well, how do we say that with an inequality? It's because f of x is greater than or equal to f of 0 for all x in the domain, which is the set of all real numbers. So this is an example of a function with an absolute minimum, and it's occurring at x equals 0. So we're usually interested in what is the x value where this is occurring. I have a couple of remarks. In this case, first remark is f has no absolute max. I'm abbreviating here. Absolute maximum, you could abbreviate it like this. Sometimes we'll just call it a max or a min. There's no absolute max because where would it occur? This function keeps going up and up and up and up forever, and to the left, it keeps going up and up and up forever. So it never reaches any kind of maximum. We could say that it approaches infinity, but we don't have an absolute maximum. There's no x value or c value that we could say the inequality in the definition is true. All right, so that's my first remark. It's possible to have a function that has no absolute maximum. It's also possible to have a function that has no absolute minimum. A quick example, if you want to know a function that has no absolute minimum, just flip this one upside down. If you flip the parabola upside down and have a parabola that opens downward, that would have an absolute max, but no absolute min. So a function, I'll say this. I'll say a function, maybe I wrote in this case, and what I'm about to say is not just in this case, so I'll say it off to the side here. A function can have one, both, or neither. Do you see how a function could have neither? Can you think of a function that has no absolute maximum and no absolute minimum? How about that? How about that function that has no absolute maximum and no absolute minimum? What does it look like when you graph that? Tiny little picture there, but you get the idea. There's no absolute. There's no greatest value and there's no minimum value. Anyway, one more remark about this case, about this example. What do you notice about this place where the absolute minimum is occurring? It's happening at x equals 0. What else special is happening at x equals 0? Maybe something involving the derivative. Look at that derivative there. We notice that f prime of 0 seems to be 0. Now, on this page, that's the first time I've mentioned the derivative. But it does seem like the place where the absolute minimum is occurring, it seems like at that place, this is the c value, isn't it? Where the minimum occurs. Seems like the derivative is 0. Do you think that has to happen? In order to have an absolute minimum, do you think the derivative has to equal 0, like a horizontal tangent line? Well, we're going to discuss that a little bit more in a few minutes. So let's not get ahead of ourselves, but we're gonna talk about how the derivative is related to extrema. So let's move on. We talked right there about absolute maximum and absolute minimum, but there are also other types of maxima and minima. So definitions. Let f be a function, and let C be an interior point. I'm going to have to tell you what that means. Of its domain, then, all right, now we want to have two definitions here. But I actually used a phrase that you might not know what that means, so maybe I need to do a definition inside this definition. What is an interior point of its domain? I'll tell you here. So this means there are points to the left and right of C in the domain. An interior point of the domain means that there are points to the left and right of C in the domain. So this is going to be relevant because we might start looking at some examples where the domain is just an interval. Maybe an interval with a square bracket on the left and a square bracket on the right. And when we start doing that, the endpoints of the domain, the endpoints of those intervals, are not considered to be interior points. We'll talk about those as they come up. But for right now, let f be a function, let c be an interior point of its domain. That's going to be almost anything in the domain. We're just kind of excluding the endpoints. Then f has a local maximum at C if f of x is less than or equal to f of c for all. Okay, this is starting to look like the definition of absolute maximum, but it needs to be different. They're not the same thing. This is going to be for all x in some open interval containing C. Do you remember what an open interval is? So I'll talk about that. There's going to be another definition here, though. F has a local minimum. Local minimum at C if it's pretty similar, right? It's just the inequality symbol is flipped. For all x in some open interval containing C. Now, what is an open interval? You've seen them before. All right, first of all, we know what an interval is. We know that an interval can have curved parentheses or square brackets. So I'm just going to say this one out loud. An open interval is an interval with curved parentheses on both sides. That's all there is to it. If an interval has curved parentheses on both sides, the left and the right, then it's open. That's all. By the way, in case you're curious, if an interval has square brackets on both sides, we call it a closed interval. All right, remarks about the above. The local maximum and local minimum are also known as the relative max or min. So if you see the word relative, it means the same as local. Another thing, this next remark's a little tricky. If the domain is an interval and C is an endpoint of the interval, we say there is a local max or min if the inequality holds on a half-open interval square bracket C comma D parentheses or curved parentheses B comma C square bracket. I'll show you an example. I think an example will help. This section, by the way, this lesson is really, because I told you that there were going to be a few lessons that all kind of go together on the same topic. So this lesson is very heavy on definitions and terminology and concepts. And yeah, that's just kind of how it is sometimes when there's an introduction to a new topic. This is kind of our overview or introduction to extreme values. Let's do an example though. I'm going to draw a function and then say some things about it. And I'm not going to give us a formula for this one. I'm just going to give us a picture and see if we can sort of analyze it based on the picture. So wait till I finish drawing this, because I want to make sure this looks right. That's going to be the scale that we're doing. Okay, I want some points in some specific places for this example. All right, this is a function that I'm going to call y equals f of x. And let's talk about extrema. Let's talk about local extrema and absolute extrema of this function. And we can tell based on the picture. We don't necessarily have to have a formula for f of x. All right, now note based on the picture, the domain of f is, what is it? What do you think the domain is? I'll zoom in. The domain is supposed to be all the x values that we can use, and this curve does not have an arrow to the left or an arrow to the right. It does not keep going. It looks like the furthest to the left that it goes is an x value of 1, and there's a dot there. And then the furthest to the right it goes is an x value of 6, and there's a dot there. So based on this, we could say the domain is square bracket 1 to 6 square bracket. It's a closed interval, meaning square brackets on both sides. Okay. We could also figure out what the range is, but we don't really need that right now. Now, let's talk about the local extrema and the absolute extrema. So I'm going to say that this function has local maxima, that's the plural, there's more than one, at. If we go by the definition, we want to look for points, or we want to look for x values where the function is greater than or equal to its surrounding values. And I'm going to say that this occurs at x equals 1, x equals 3, and x equals 6. Look at the curve at all three of those x values. Let's just start. At x equals 1, the function is greater than or equal to its surrounding values. And this is actually using that last remark I made. The domain is an interval, and C is an endpoint of the interval, so I only really had to consider the inequality on this direction, because there's nothing to the left of it to consider. So yes, that is a location where a local maxima occurs. There's a local maxima at x equals 1. There's also one at x equals 3, because that's the top of this hill, and the surrounding values are less than or equal to it. And then there's a local maximum at x equals 6, again, because the neighboring values on the curve are less than or equal to it. How about local minima? So I think there's more than one of these as well. What do you think? There's two of them. This is going to happen at x equals 2 and at x equals 5. Because if we look at the curve, you can see that at x equals 2, we are at the lowest point of this valley. The neighboring values are greater or equal to. So this is less than or equal to its neighboring values. And then at 5, the curve is also, the function value is less than or equal to its neighboring values. We're at the bottom of this valley. Let's talk about absolute. Absolute maximum. At. All right, so it's going to be x equals something. Yeah, we're looking for the highest point on the curve, and this is going to be here. This looks like the largest f of x value that occurs, so it happens at an x value of 1. There's an absolute minimum. Oh, by the way, when you find the absolute maximum, just quickly check to see, are there any other places that are sort of tied for first place? You know, is there anything else that's also equally this high? And no, there is not. So there's just the one. Absolute minimum at x equals 5. That's the lowest point on the graph. And there's nowhere else on the graph that gets that low or lower. So that example and that discussion, we were mostly interested in the x coordinates of where these things happen. What about the y coordinates? All right, so we listed the x coordinates where these extrema occur. What about y values? Do we care about the y values? So let's talk about that. We say the absolute maximum value of f is 3. And the absolute minimum value of f is 0. So I can just barely fit all this stuff on the screen, but I'm going to try to... We'll just cover up the domain there. All right, so you can see the curve, and you can see what I'm saying about it. I'm going to point to some stuff. Over here, I said the absolute maximum occurs at x equals 1. The absolute minimum occurs at x equals 5. We talked about those. X equals 1, x equals 5. It's kind of the places where interesting things are happening. Here, I'm phrasing it a little bit differently. Notice that up here, I used the word at. There is an absolute maximum at this x value. But down here, I used the word of. So you have to be a little careful about at versus of. The absolute maximum value of this function, of f of x, is what is the largest value that f of x ever gets to. F of x is 3 here, right? F of 1 is 3. I'll write that. Because f of 1 equals 3. These are the y values, and this is because f of 5 equals 0. That's the lowest that f of x ever gets. So I think that we are usually, in these sections, usually we're going to be more interested in the x coordinates. So a lot of problems are going to say, like, find the x coordinates of the local extrema, or find the x coordinates of the absolute extrema. And you know extrema means maxima and minima, both of them. But you could get a problem that says, what is the absolute maximum value of this function? And in that case, it's asking you for the y value, because it's asking you for the function value. So be a little bit careful about that. Now, I want to get back to something that I was mentioning earlier about the derivative. You know, in that one example that was just a parabola, I said that there was an absolute minimum, and where the absolute minimum occurred, it looked like the tangent line was horizontal. It looked like f prime was going to be 0. And I guess we could look at this picture and look at where the local maxima occur, the local minima occur, you know, and a lot of these places, in a lot of them, it looks like the slope of the tangent line would be 0 at the bottom of this valley, at the top of this hill, at the bottom of this valley. So I'll draw that in here. So you might start to think, can we locate x values of maxima and minima by looking at the derivative of the function and finding where does the derivative equal 0? Let's talk about that. So I have a couple of questions for us to think about together. If f has a local min at x equals c, must f prime of c equal 0? It's just a yes or no question. Do you think, in general, not just for the function that we drew a minute ago, but for any function, if there's a local minimum at x equals c, do you think that the derivative has to equal 0 there? The answer is no. And I'll show you what we call a counter example. Show you a reason or an example of why this is no. Consider this function. Do you remember what this function is? Looks like the letter V. This is the function f of x equals absolute value of x. It has a local min at x equals 0. Because at x equals 0, the function is less than or equal to its surrounding values. In fact, that local minimum is also an absolute minimum. But what is f prime of 0? Well, I was about to write an equal sign, but actually f prime of 0 does not exist. Do you remember way back when we first learned about the derivative? We learned there are a couple of cases where the derivative doesn't exist. And one of them is the derivative doesn't exist at sharp corners. In fact, I probably used the absolute value of x as an example back then of a sharp corner where the derivative doesn't exist here. So the answer to this is no, because f prime of 0 does not equal 0 here. Okay? So the answer is, not necessarily. It doesn't have to equal 0. Another question for us to think about is the other way around. If f prime of c equals 0, must f have a local min or local max at x equals c? So this time I'm asking the question the other way around. What if we know that f prime is 0 somewhere? The slope of the tangent line is 0 somewhere. Does that mean that the function has to have a local minimum or a local maximum at that place? Just want you to think for a sec about whether you think that's yes or no. So this is no. And I'll give you an example, or we could call it a counter example. There are many examples of this, but I think my favorite example of this is, this will be an approximate picture, I guess. Do you know what function I'm drawing? Might not be perfectly to scale. That's okay. This is the function f of x equals x cubed. And, all right, so from this function, notice that f prime of x is 3x squared, right? We know that derivative. So f prime of 0 equals 0. That means that if I drew this just right, we could look at 0, the origin, and we could draw the tangent line, and it would actually be horizontal if I drew it just right. At that moment, if you zoom in on the function right there, it looks like the curve goes horizontal just for a moment before it starts increasing again. Pretty cool. But there is not a max or a min at 0. It's not a max or a min. It's on its way. It keeps going up and up. It's not the top of a hill. It's not the bottom of a valley. In fact, this is an example of a function that has no extrema. There's no local max. There's no local min. There's no absolute max. There's no absolute min. This is a function that has none of those. So, okay, it seems like I asked two questions about how the derivative is related to minima or maxima, but the answer to both of them was no. So it's starting to seem like, is the derivative related? Like, what can we say? This is what we want to know is, so what can we say about maxes and mins and how they relate to the derivative? Like, do they relate to the derivative at all? It seems like they don't have to. So we have a theorem to answer this. And we'll see that they actually are related if f has a local max or min value at an interior point C of its domain, and I'm underlining that, if f prime of C is defined, then f prime of C equals 0. All right, that's the missing piece. When we were looking at those questions above, this is kind of the missing piece that we didn't have in those questions. If this happens and if the derivative is defined, then it has to be 0. So in that example above that I've already moved off of the screen, we had one where the derivative did not exist. Now we're saying that if it does exist, it has to be 0. Okay, so we have a definition now. So this is good. This theorem is good because it seems like maybe if we find all the places where the derivative equals 0, it doesn't necessarily mean that we are finding the locations of extrema. Let me remind you, this sort of situation can happen. So if we find all the places where the derivative equals 0, we're not guaranteed to be finding a max or a min. However, we are finding places that are candidates for being a max or a min and are worth further investigation. And we have a name for these places. An interior point C of the domain of a function f where the derivative is 0 or the derivative is undefined. These are the places that are kind of the candidate locations of where we might find a maximum or a minimum. It is called a critical point of f. I'm going to underline critical point. So we're going to see some problems coming up that might say something like find all the critical points. And when you find all the critical points, those are the places that might have a local maximum or a local minimum. And we're going to talk about how to find whether it really is or not. But it would be easy to find these places, right? You know how to find derivatives. You could set the derivative equal to 0 and then solve. Before we do any of that, I have to tell you that this is also known as critical number. And we might use those two phrases interchangeably. So if we say here's a function, find the critical points, or if I say here's a function, find the critical numbers, it's the same thing. It's the C values that we're interested in. This theorem and this definition and the discussion that we've had so far kind of leads us to a procedure for how to find absolute, max, and min values of f if we are given a function f defined on a closed interval. Remember what a closed interval means? It means an interval with square brackets on both sides. There's a procedure. It's going to be 3 steps. Step 1, find all critical points. And I'm going to say, well, I'm just going to leave it at that. But I want to point out something to you. Look at the definition of critical point. It says that a critical point, an interior point C of the domain of the function, it has to be in the domain of the function. So if we're given a function with some small closed interval, square bracket 1 to 6, or square bracket 2 to 10, or whatever it is, the critical points we find, we're only going to consider the ones that are in the domain. They have to be in the domain to be considered a critical point. Okay. Step 2, evaluate f at all critical points and endpoints. When I say endpoints, I mean the endpoints of the domain. The domain is a closed interval. It could be square bracket 1 comma 6, square bracket. You know, we need to check the endpoints because that could be a place where an absolute max or min happens. And then finally, step 3, take the largest and smallest of these values. So we'll do a couple of examples. But that is going to be our 3-step process for this type of problem. When you're given a function, it's on a closed interval, and the problem says find the absolute maximum and minimum values of the function. Remember when we say the maximum and minimum values of the function, we're interested in the f values, right? Not just the x coordinates. Okay, let's get started. Let's do an example. I'll do the first one. Find absolute max and min values if there are any of f of x equals parentheses x squared minus 1 to the third on the interval square bracket -1 comma 2 square bracket. So I said that I would do this first one for us, but that is the question. We're going to do this without graphing it. I know that we've looked at some graphs today, but this function doesn't seem easy to graph, so we're just going to do this based on this 3-step process. Now, to find all critical points, it seems like we need to find places where the derivative equals 0 or where the derivative is undefined. Well, in order to do that, we need to find the derivative. So that's kind of built into this problem. It's built into step 1 that we need to find the derivative. So, step 1, I'm going to write critical, do we want to call it critical points or critical numbers? Either way. All right, we're going to work on finding critical points. In order to do that, we need the derivative. And this is a chain rule problem, right? So do some scratch work off to the side if you want, or if you can do the chain rule in your head, that's great. I know that the 3 is going to come down out front, and then we get 3x squared minus 1, and then it's raised to the 2. But because of the chain rule, we have to do times the derivative of the inner function. So that's times 2x. And we could write this more simply by combining the 3 and the 2 to make 6. And I think I'm going to bring the 2 and the x, I'm going to bring both of them over here to the left. So let's make this 6x x squared minus 1 squared. How's that? We want to find places where this equals 0 or where this is undefined. This looks to me like it is always defined because it's a polynomial. So I don't think we're going to find any critical points that way. But we could look for some places where this equals 0. So I'm going to set this equal to 0. Set it equal to 0. And then what do we get? Well, 6x, we could say x equals 0. And then what about this? X squared minus 1 equals 0. This suggests that x equals -1 or x equals +1. So we found a few different x values here. I'm going to circle some of them, but not all of them. Let's talk about this. For each value of x that we find, is it really a critical point? X equals 0 is an interior point of that domain. So yeah, that's a critical point. All right, crit point. What about x equals -1? Is that an interior point of the domain? So that's kind of the little subtlety that's going on here, is technically this is an endpoint, and it doesn't really fit the definition of a critical point because it's not an interior point. It doesn't have points to the left and right of it in the domain, so I'm not going to circle it. I am going to circle 1 and say that this is a critical point. So if you just asked me to find all the critical points or critical numbers, I would say x equals 0 and x equals 1. Let's move on to step 2. Also, when you're doing this process, if you find anything that's just like blatantly not in the domain at all, like if you found x equals 3, just throw it out. You're not going to use something that's not in the domain. We can't possibly have a maximum or a minimum value occur outside of the domain. So, yeah, this is the moment when you would check that. There was something that I said out loud that I think I want to put it in writing. I just want to say, note, f prime always exists in this case. We can find critical points sometimes by finding the derivative and looking for places where it's undefined. That might happen if you have something like a denominator and you don't want the denominator to be 0. You might find critical points that way, but it's not happening in this problem. All right, let's move on to step 2. Step 2 is the evaluate step. It says to evaluate the function at all critical points and endpoints. So at the critical points, we evaluate f. So f of 0, we're going to find out what that is. And f of 1, we're going to find out what that is. And we also need to evaluate it at all endpoints. The endpoints are the endpoints of this original interval, so -1 and 2. So f of -1, f of 2. It actually doesn't matter which order you do these in, as long as you check all 4 of these. So I'm going to move the other page away now. Oh, I'll point to one thing before I move the page away. Notice that I'm doing f of 0, f of 1, f of -1. We have to go back to the original function that was given in the problem. It's not the derivative that we're putting these into. It's the original function. So x squared minus 1 to the third. What happens when you put 0 into that? Put 0. 0 squared minus 1 to the third. That's going to be -1. What happens when you put in 1? 1 squared minus 1 to the third is 0. Put in -1. -1 gets squared, and then -1 to the third is 0. And what's f of 2? F of 2. 2 squared is 4. -1 means it's 3. 3 raised to the third power. What's 3 to the third? 27. Okay, that's it for step 2. Step 2. Now, step 3. Step 3 is where we find the result. Step 3 in the process says take the largest and smallest of these values. Oh, I can see what the largest and smallest of these values are. So the result is that the absolute minimum value of f is -1. And the absolute maximum value of f is 27. The function never gets smaller than -1, and it never gets larger than 27. At least not on this domain that we were given. Okay, so this isn't that hard. It's not that bad, right? You find the derivative, you evaluate the function. Well, okay, you find the derivative and set it equal to 0, and then you find critical points that way. The critical points remember, I said that those are kind of like considered candidates. Those are places that might have a maximum or a minimum. And even though we answered the problem, I just want to point something out to you. I want to point out to you that this happened at the critical point x equals 0. That's where that occurred. And this occurred at the endpoint x equals 2. F of 2 was 27. And the reason I'm pointing this out to you is because I wanted to make it clear that this is why it's important that we check both the critical points and the endpoints. Because all 4 of these numbers were potential places where we could find an answer. And it turned out that, yeah, one of them was at a critical point and one of them was at an endpoint. Sometimes you get a problem where both of them are at endpoints or both of them are at critical points. But yeah, we need to check all of it. And you could get a problem that has more than 2 critical points. You could get a problem that only has 1 critical point. However many there are, you need to check all of them in step 2. So I have a problem I want you to try that's the same type of problem, just a different function and a different domain. So I'm going to ask you to find the absolute max and min values of the function f of x equals 10x times 2 minus ln x on this closed interval. So I'd like you to pause the video and give this a try. Okay, so I think in this example, finding the critical points is a little bit harder. But that's step 1. Step 1 is to find the critical points. And you could say that finding the derivative is really the first thing to do, because we need that. So f prime of x. This is a product rule problem. We haven't done the product rule in a while. 10x times 2 minus ln x. So first function times derivative of the second one plus the second function times derivative of the first one. Let's simplify this. 10x times negative 1 over x is negative 10. And then let's distribute this. 2 times 10 is 20. And then minus 10 ln x. Negative 10 plus 20. Let's simplify this. Simplify before you go further, right? So this is 10 minus 10 ln x. It's going to be easier to work with if you simplify it. Okay, that is f prime of x. I guess you could factor out a 10 if you want. So what do we do once you find the derivative? Well, do what I did in the previous problem. Set it equal to 0 and solve for x. Okay? Set equal to 0 and solve for x. Oh, by the way, you would also, at this point, since you found the derivative, you could also look for places where the derivative is undefined. Like, are there any x values where this is undefined? I see ln, which is a logarithm, and I know that we're not supposed to do a logarithm of a negative number, or 0 for that matter. But the domain we were given is all positives, right? 1 is positive, e squared is positive, so everything in between is positive. So we're not going to find any x values in the domain where this is undefined. But we might find some x values in the domain where this is 0. Now that we're setting this equal to 0 and solving, I think I'm going to divide both sides by 10. Got that. That was good. Let's rearrange this then. We just get, what, ln x equals 1? So do you know what x equals? What does x have to equal to get ln x to be 1? There's only one value where that happens. X equals e. Is this a critical point? We need to check to see, is it an interior point of this domain? Is it between 1 and e squared? Yes. Yes, this is a critical point. We only found 1 for this problem, but e is definitely, it's around 2.7, right? So it's definitely bigger than 1, and it's definitely smaller than e squared. So we found a critical point, and all of that was step 1, and now we can move on to the evaluate step. We need to evaluate f, the original function that was given in the problem, and we need to evaluate it at critical points. Here, I'll label it. Critical points and at endpoints. So we need to do f of e, and we need to do endpoints, which are going to be f of 1 and f of e squared. Like I said, you could check these 3 in any order as long as you check all of them. Put this into the original function. You get 10e times 2 minus 1. That equals 10e. Put 1 into the original function, and you get 10 times 2 minus 0. 10 times 2 minus 0 is 20. Put e squared into the original function. You get 10 e squared times 2 minus ln e squared. Can you see what that equals? We can do this by hand. You don't need a calculator for any of this. Look at this. Ln of e squared, I know because of logarithms. You know, what does ln mean? What does e to the power mean? You know that they are inverses of each other. So ln of e squared is 2. You learned that at one point in an algebra class or a pre-calculus. Ln of e squared is 2. So in parentheses here, we have 2 minus 2, which is 0. So the whole thing is 0. We can write the result now. Well, can we write the result? Okay, at this point, step 3, you're supposed to take the largest and smallest of the values that we found. So absolute min value. Out of these 3 numbers, which one is the smallest? 0. Absolute max value. Out of these 3 numbers, which one is the largest? It's not 0. Which one is larger, 10e or 20? Like I said, we can do this without a calculator. I would like you to know that e is approximately 2.7. You don't have to know all the digits. I mean, nobody knows all the digits. It goes on forever. It's one of those numbers like pi that you can typically just work with an approximation. So anyway, e is around 2.7, so 10e is approximately 27, which means that it is the largest one. So 10e is the larger one, and that's going to be our answer. And this problem didn't really ask us to give the x-coordinates of where the absolute max occurs and where the absolute min occurs. But if you needed to, we found it along the way. I mean, we can say this occurs at e squared, so at x equals e squared, and this is happening at x equals e. So it turns out in this problem, one of the answers occurs at a critical point, and one of the answers occurs at an endpoint. So it's a good thing we checked both types. Plus, it was just a good derivative practice problem. Taking this derivative and setting it equal to 0 and solving, That was all good practice. So that's it. That's going to be it for this section. We learned a lot in this section. We learned about absolute maximum, absolute minimum, local maximum, local minimum, and critical points. Right. So we did quite a lot. And remember, like I said at the beginning, there is a sheet with a bunch of those definitions all in one place, so you could have that with your notes. So the next two lessons, I think, are going to sort of continue doing more stuff with maxima and minima. All right, so we'll see some more of these things. That's it for now. Take care, and I'll see you soon.